Okay, so the instructions read here that we need to sketch the graphs of the following functions, find the intervals where the functions are increasing or decreasing, the intervals where the functions are concave up or down, and any inflection points. So here to start, we have this A. So what I'm going to do is I'm just going to draw my axes to start, and just to get a sketch and a very rough sketch here, right? I'm going to start off with simple points. So when x is 0, y is 3, so 1, 2, 3. So this is a point on the curve, and then maybe when x is -1, right, what do I get? -1 is -3, plus 4 is 1, plus 3 is 4, so I have this point, right? Make sure I did that right. -1, -3, negative, negative, positive 4, that's 1, plus 3 is 4. Okay, so it's 4 up here. And -1, and then at 1, let's say 1 is going to give me 3, minus 4 is -1, plus 3 is 2, so it's somewhere over here. Okay, now with this, I have some points on the curve, whatever. Let's find out where it is that this function is increasing and decreasing. So to do that, the first thing you want to do is you want to compute f prime of x. So f prime of x is 9x squared minus 4. Right? I bring down the 3 and multiply it by 3, I get 9. The exponent decreases by 1, minus the derivative of 4x is just 4. The derivative of 3 is 0. Now, what you do is you set your derivative equal to 0 and you solve for when it's equal to 0. This here is the difference of two squares. This is 3x squared minus 2 squared. So it factors as 3x minus 2 times 3x plus 2 equals 0. This gives me two values for when it's 0 at 2 over 3 and x equals -2 over 3. So -2 over 3 and 3, 2 over 3, I'm going to put points. I'm going to make them right here is -2 over 3, and then right here is +2 over 3. And this is where the derivative equals 0. So when I draw out this sketch here, right, when I draw out this line, I'm going to put 0 right here. I'm going to put -1 over here. -2 over 3 is somewhere over here. I'm going to put 1 over here, and then +2 over 3 is somewhere over here. And I'm just going to test the intervals that I have now, because we should see that the intervals that I've broken up the real line into 3 intervals. Everything less than -2 over 3, between -2 over 3 and 2 over 3, and then everything greater. Those are the 3 intervals, and you just test what's happening to your derivative in these 3 intervals. So you start off with this, you go here, you say, okay, so -1 is to the left of -2 over 3, so you just test, they use that as a test point. My derivative is this, so f prime of -1, right, is, if I do 3, if I use this factored form, so remember f prime of x, when I factor it, it's 3x minus 2 times 3x plus 2, right? If I do f prime of -1, then I'm going to get negative, this is going to be negative, times, this is going to be -3, negative, so the whole thing is positive. So that means that my function is increasing all here. Okay, it must be the case that it's increasing all there. Now I pick a point between -2 over 3 and 2 over 3, which is 0. 0 is a good test point. I plug in 0 to this, I'm going to get -2 times +2. And when I plug in f prime of 0, and -2 times +2 is negative, so this is all decreasing, and my function's decreasing on this interval here. And now I pick a test point to the right of 2/3, and that'll test my final interval. And if I do f prime of 1, I'm going to get, this is 1, this is 1, it's positive times a positive, so it's positive. So that means my function is increasing on this interval. And now I know where my function's increasing and decreasing. My function is increasing, right? You could say increasing on from -infinity to -2/3. And union, it's increasing from +2/3 to infinity. And it's decreasing only in this interval from -2/3 to 2/3. At -2/3, it's not increasing or decreasing because your derivative is 0. Your derivative is 0 at these 2 points. So it's not increasing or decreasing on this interval. And with that information, you could start to sketch what your curve actually looks like. You can plug in this negative 2/3 into the original function, right? So if I take my time, 3 negative 2/3 cubed minus 4 times negative 2/3 plus 3. And let's see how ugly this looks. This is going to be 3 squared negative 2 cubed minus or plus 8 over 3 plus 3. And then this becomes negative 8 over 3 squared plus 8 over 3 plus 3. And then this is going to be times 3 squared. This is going to be times 3 cubed, 3 squared. And then the whole thing is over 3 squared. And then this becomes negative 8 plus 8, 6, and 24 plus 27 over 3 squared. This is going to give me 16 plus 27. Ugh, this is terrible. It's 13, 3, 43 over 9 is my answer for what this one is. So negative 2 comma 3, if I did this math right, and you guys can check my arithmetic, maybe this is an error. 43 over 9 is 9, 18, 27, 36. 4 and 2/3. So this is going to be up here, like right there, okay? And with that, right, once I have that point's where it is and what happens, well, my function is going to be increasing, and then it's going to reach its max right there. Here, it's a max, and then it begins to go back down, 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 to wherever this is going to be, the 2/3. So you plug in the 2/3 to get its point. So what's going to be that point? So let's see, 3, and now I'm plugging in positive 2/3. Wait, did I plug in negative 2/3 before? I hope so. That's negative. Yep. And then that was negative. Okay, it was positive. Good. Okay, we should be good. Hopefully that's not an error. But let's see. 4 and then 2/3 plus 3. I'm going to get, again, 2/3 over 3 squared minus 8/3 plus 3. This is going to give me times 3 squared and then 3 cubed over 3 squared. And I'm going to get 3 squared over 8 minus 8, 16, 24 plus 27. I'm going to get negative 16 plus 27 is going to be negative 16 plus 27 is 7. Negative 16, no, is 11 over 9. And 11 ninths is 1 and 2 ninths. So 1 and 2 ninths is, let's say, somewhere over here. And then it bounces up, and that's sort of a local min, we call that. And then it just increases again without bound. And this is something like what my function will look like. It also asks, where is it that this is concave? And with this initial sketch, it's going to help us. We're going to get some confidence in how we determine concavity. So let's go and get a new piece of paper, and let's just go back and forth between these two. So I have, again, let's write my function. My original f of x is 3x squared minus 4x plus 3. And I want concavity now. So my first derivative is 9x squared minus 4, which is the same thing as 3x plus 2 times 3x minus 2. And then I'm going to take the second derivative. I differentiate this, I'm going to get 18x. And that's my second derivative. I set my second derivative equal to 0. And I get that x equals 0. And then I draw the line again. So now I have, again, this line. This 0 point is going to be the key. It divides the interval into two parts. Everything less than 0 and everything greater than 0. So less than 0, f double prime is negative. And greater than 0, f double prime is positive. So that means that my function is concave up here. Concave down, because my second derivative is negative, concave down. And then over here, it's concave up. And it's switched its concavity at 0, which means that this x equals 0 is inflection point because it changed its concavity at that point. And with that, we can look, and let's go back to our rough sketch here, and let's see. So basically what they're saying is that the tangent lines, so what happens? So let's look at a tangent line, right? Here, first of all, it's above the curve, right? Above the curve. So it makes sense to say that it's concave down all here. And basically, the tangent lines are decreasing, right? Here it's very positive at this first point that I picked. The slope is very positive. Then it's less positive. Here it's 0, and then here it's negative. But then at 0, if you look, the tangent line is neither above nor below the curve, and the tangent lines then begin to change their direction. So here, this is a very negative slope, but then here it's less negative, and then here it goes back to 0. And then here you see that the slope of the tangent line keeps increasing as you go along. So that follows along the line. And this point at 0 is indeed an inflection point. The concavity switches. Okay, inflection point. And now, so that's basically what they wanted. We have the two things. You could also just say this is, F prime, this point right here. You could use the same thing. F prime is this. Right, and then you could say F double prime, and you could say that, what is it? It's going to be concave down all here, and then concave up all here. And you have an idea of what this curve would look like. Let's try and do one more. Okay, B is a good one because it's no longer a polynomial. It's a rational function. It's the division of two polynomials, but it's a nice rational function because it's defined everywhere, because x squared plus 2 can't be 0. And because it can't be 0, we're in good shape to say that its domain is all real numbers, so we won't have anything funny happening. Let's compute the first derivative. Let's see what we can do. Again, we want to look for where it's increasing or decreasing in the intervals where the function is concave up and concave down, and we also want to sketch this. So let's go through this. Okay, so here's my axes. And again, I'm going to start off just plugging in what's happening at the y-axis. This function is defined everywhere again. So when I plug in 0, I get 0. So this is a point, right? When I plug in x as being 0, I get 0 over 2, which is 0. I'll plug in 1. Let's see what I get. I get 1/3. So 1, let's say that this is 1/3. So 2/3, 3/3, this is 1. 1/3. And then negative 1. If I plug in negative 1, do I get the same thing? No, I get negative 1/3. Okay, so that's an error. So let's go back. So when I plug in negative 1, I get negative 1/3. So let's do that. So let's say that's negative 1/3. So this is 1. This is negative 1, sorry. And then this is negative, this is positive 1. And then 1 over here is 1/3, right? So let's check that. 1 gives me 1 squared plus 2, which is 1 over 1, which is 1 over 3, which is 1/3. And then when I plug in negative 1, I get a negative 1 in the top, and then the bottom is still positive 3. So this is all good. Everything here is good. Now, let's see. So now that I have this idea, this is f of x, right? Let's compute and let's find out where it is that this function is increasing or decreasing by computing the derivative. I'm going to do quotient rule. Quotient rule says that the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. Okay, and that's my derivative. Now, I want to solve for when this function equals 0. I'm going to simplify the top. Now, we want to know how to simplify, because now we actually need to solve equations and do stuff like that. So simplifying is going to help us out. This is going to become negative x squared plus 2 over x squared plus 2 squared. And what I have here now is that I want to make this function equal 0. I want to solve for where it is that this is 0. The bottom is never 0, so we're actually in good shape again. Because, oh wait, yeah, the bottom is never 0. You can never make x squared plus 2 equal 0 among the reals. So we're okay in that case. All we need is the top to being 0. So this, again, this equation is true if and only if negative x squared plus 2 equals 0. And then this means that x squared is going to equal 2, right? And that means that x plus or minus the square root of 2 is when it is that this function is 0. And at this point now you want to draw out your number line. You want to say, okay, so the square root of 2, here's 0. So here's negative 1. Here's 1. And then let's say here's 2, right? The square root of 2 is between 1 and 2. So I don't know, maybe here is the square root of 2, positive. And then maybe here is the square root of negative 2, or negative square root 2. And again, this breaks up your interval into, this breaks up the real line into 3 different intervals. Everything less than the square root of, or everything less than the negative square root of 2, everything between negative square root 2 and positive root 2, and everything greater. Those are the 3 intervals that you have. So you just pick test points to plug into your derivative. This is probably the most simple version to plug into your derivative in this case, but you can simplify this process and speed it up by realizing that the bottom is always positive. So given the fact that the bottom is always positive, you just need to test the top, because then that means that if the top is negative, the whole thing is negative. If the top is positive, the whole thing is positive. So my first test point that I'm going to do is I'm going to test this interval, right? Everything to the left of negative root 2. So I could just test 2 here. So 2 is going to give me what when I plug it into my derivative? F prime of 2. Well, it's going to be, or negative 2, sorry. Negative 2. If I plug in negative 2, I'm going to get negative 2 squared is 4, and then it's a negative in the front. So it's negative over the positive, which makes it negative, the whole thing. And that means that my function is decreasing all here. Okay, now I pick a point between negative root 2 and positive root 2. I'll pick 0. 0 is going to give me positive 2, so my function is increasing all here. And then I pick something greater than root 2, which is 2. And then that's going to give me 2 squared is 4. Negative is on the outside, so it's negative 4 plus 2. And then that means that this is all going to be negative. And now I have where my function is decreasing here, increasing here, and decreasing here. And you could write that out on an interval notation, but right from here you could sort of maybe get a sketch of what your curve actually looks like. There's a key thing from pre-calculus that we should know or remember, which is that this has a horizontal asymptote, which will help us immensely. So what does that mean? The limit, let's talk about horizontal asymptotes in general. The limit as x goes to infinity in either direction, okay, is 0, because this bottom piece grows way faster than this piece. So it's going to tend towards 0 in either direction. So that means that you're going to have this asymptotically approaching the x-axis. And that helps us out because that means that since it's decreasing on this interval over here, right, from here to here, what you have is that it's getting, so what's happening from here to there if it's decreasing? That means that, how does this look? Because you want it, oh, the negative 1 means nothing, so it's root 2 that I care about, negative root 2 over here, and then positive root 2 over here. So it's decreasing, and then at root 2, what happens? So at root 2, it's root 2 over 2 plus 2, which is just root 2 over 4. So root 2 over 4 is some positive value that's like up here. So what's happening? It's decreasing. It's decreasing at this point. How could it be decreasing to get to here? So you see, you got to take your time. What's wrong with, what's the mistake in my logic? It has to be that this function, if it's decreasing, right, decreasing, that means that it has to come from up here and go down like that. How's that possible? And then increasing. What did I do wrong? Did I calculate the derivative wrong? X squared. The derivative of x is 1 times the first function minus the derivative of the other function is 2x times the top is 2x squared. This is 2x plus 2 minus 2x squared, which is negative x squared. Which is negative x squared. This whole thing squared, that's always positive. This here, when I plug in something like negative 2, it's going to give me this. Negative 2 squared is positive 4. Negative 4 plus 2 is negative. The function is decreasing on this interval. If the function is decreasing on this interval, then what do I get when I plug in negative? Oh, it's negative. Okay, yeah. Negative root 2. That's why. This is negative root 2. And then this is 2 plus 2. It's 4. The whole thing is negative. Okay, now it makes sense. Because you see what's happening. It looks like this. It's getting closer and closer to 0, right? That's the horizontal asymptote. And then it sinks down to hit this negative root 2 over 4 right here. And then it goes through here. It's going to come up. It's increasing all in this interval as it is here. Look, from here going through. It's increasing, and then boom. At this point, right? So not at this point, at this point right here, it hits its max, and then it goes back down. And it decreases all the way for forever after that. And then that's how it looks. This is what your sketch roughly looks like. So my mistake was that I didn't see that this was negative right here, this one. And that's what threw me off, because I was wondering how it could come from down here while having that horizontal asymptote. So it takes some knowledge from pre-calculus to get this curve at this point where it looks like this, because you want to know about that horizontal asymptote right here. And that's not so easy. But with practice, we should know, right? The horizontal asymptote is just computed by this limit. So this limit says limit as x goes to infinity. This is how you would compute the horizontal asymptote of f of x, right? And there's a few cases, right? This limit could not exist. It could go off to infinity. It could equal 0, or it could equal some constant, not 0. And there's cases for this, right? It goes off to infinity if the degree of the numerator of f of x in this case, right, is x, which is 1. So the degree of the numerator is less than the degree of the denominator, which is x squared. And if the degree of the denominator is greater than the degree of the numerator, it goes towards 0, like in this case, right? The degree of the denominator is 2, the degree of the numerator is 1. So the horizontal asymptote is y equals 0. It approaches the x-axis, like in this curve that I sketched here. But okay, now that I have the curve, let's go through the actual calculus. The rest of the calculus is computing the second derivative and finding out where it's concave up and concave down. And we're going to match that with the sketch that I just did. So I have, again, f prime of x is equal to x over x squared plus 2. Sorry, that's f, not f prime. So f of x is equal to x over x squared plus 2. And then f prime of x is equal to the derivative of this is x squared plus 2 minus the derivative of the bottom times the top is that. And then the bottom is squared. This simplifies to negative x squared plus 2 over x squared plus 2 squared. And again, I'm going to have to do quotient rule on this. I'm just going to have to take my time. The derivative of the top is negative 2x now, times the bottom is x squared plus 2 squared, minus the derivative of the bottom by chain rule is 2 times x squared plus 2 times the derivative inside is 2x by chain rule, times the top function, negative x squared plus 2, over the bottom function squared, which is x squared plus 2. Squared, so it's to the fourth. Okay, so be sure you check this, take your time. Maybe I made a mistake as well. I'm going to have to do the algebra and simplify a little bit. So I see that I have an x squared plus 2 here. So maybe I'm going to factor that out. I'm going to call this whole thing z. Right, this is z squared. This is z. So what do I get? I'm going to get negative 2xz minus 4x. When I factor out the z, 4x minus x squared plus 2. And then the z is on the outside. And then this, again, is z. So it's z to the fourth. And then this z and this z cancel. And I'm left with a z cubed. And then this becomes negative 2xz minus 4x negative x squared plus 2 is f double prime of x. And then now let's go back for z and distribute because I don't see any other way. Now that the bottom is cubed, we may have to consider, can it be, oh, it still can't be negative, so that's good. The bottom is still going to be positive, but let's see if we can simplify the top a little bit more. So now I got negative 2x, z is this x squared, plus 2 minus, or plus 4x cubed minus 8x over 2x squared plus 2 cubed. And then this here is going to simplify a little bit more. Negative 2x cubed minus 4x plus 4x cubed minus 8x x squared plus 2 cubed. And then we get that this is going to be 2x cubed, cancels, minus 12x over x squared plus 2 cubed, and then I'm going to factor out a 2x to make it as easy as possible. X squared minus 6 over x squared plus 2 cubed. Hopefully I did my algebra correct. This is f double prime of x, as simple as I can make it. It's not too bad to draw out this number line because, again, the bottom is always positive. So since the bottom is always positive, testing points and finding out when it is. But, I mean, it is a little ugly because actually if you solve this for 0, you get that ugly square root 6. But that's fine because, look, you have it 2. You want to make this top part 0. So 2x x squared minus 6 equals 0. When x is 0, and when x is equal to the square root of 6, and when x is equal to the negative square root 6. And these are the three values that you have to break up this thing into. So it's 0, negative root 6, wherever that's going to be, and then positive root 6. And now those 3 points break up this interval into 1, 2, 3, 4 intervals, right? So the whole real line now is broken up into 4 intervals. You're going to need to choose test points for these things. So negative root 6 I know is greater than what, negative 3? Sure. I mean, negative 3 is fine. So negative 3 is over here. You plug that into your derivative. The top part, again, is always positive. So you only have to check the top part. The bottom part is always positive. So you can plug into the top part. The top part is going to be, this is going to be 9 minus 6, so this is positive. And then this one's going to be negative. So here, your function, the second derivative I found out was negative all here, which means that it's concave down all here. Then, between negative root 6 and 0 is negative 2, and you plug that in. You're going to get negative 2 squared is positive 4 minus 6 is negative 2. And then this is negative because it's negative 2 times negative, because it's negative 2 times positive 2, which is negative. So here it's concave up all the way to 0. So concave up. And then you got to check between 0 and root 6. That's positive 2. Let's see what happens with positive 2. This is positive. This is negative, so it's negative here, so it's concave down. And you just have to sit here and be careful with this. I might have made a mistake, who knows, like, again, sit here, this is the procedure. The arithmetic is tedious, it's all about bookkeeping, and it just takes practice. I'm doing this quick, so take your time. 3, I plug in 3, I'm gonna get, this is positive, so this is all positive, and it's concave up here. And with this, let's match that with the graph that I just drew. So negative root 6 and root 6 and 0 are all inflection points. And let's match that with what I drew over here. So if you look, right, the slope, the tangent line is above the curve all here. Up until some point over here, which we discovered was negative root 6, it inflects. So these are inflection points because now the tangent line is beneath the curve. And then at 0, you should see that it also inflects again, and the tangent lines are above the curve. And then it inflects again at positive root 6 right here, where it's like the tangent line at that point, it kind of lies like right on top of the curve. And then after that, it's beneath the curve. And that matches everything that we have from computing the second derivative. And this curve is indeed accurate. The most difficult part of this problem is for sure the fact that you needed to remember from pre-calculus that there's a horizontal asymptote here. But now that we have the calculus and we have limits, we should see that the limit as x goes to infinity of this function, which is just x over x squared plus 2 equals 0. And it's true for plus or minus infinity. In either direction, you should convince yourself that this, as x gets really negative, tends towards 0, and as x gets really positive, it tends towards 0. And that's the most difficult part about this, because it's removed from all the calculus, right? We have to remember from pre-calculus, now we're putting it into a calculus setting.